All right, it's me again. I'm lucky enough to be wrapping up the talks portion of the conference by talking about crash reports. So this talk is broken down into two parts. We are going to try to gain a deep understanding of crash reports on macOS. And with that understanding, we can show that we can do all sorts of neat things, such as uncovering malware, vulnerabilities, failed exploitations, and more. As mentioned on the slide, that we will be focusing on crash reports. We'll also touch on some other tangential topics, so I hope you learn some of this as well. Really, though, my main goal is that I want you to come away with a deep appreciation, if not love, for crash reports. I think they are something that needs more attention and more love. Now, you might be wondering, Patrick, why are you even talking about this? Who cares about crash reports? Well, everybody does. First, and we'll walk through this, by crash reports, users can report bugs to developers. Developers who want to fix bugs in their software, the best way to do that is with the crash reports. Security teams, as we can see, chopped off a little bit, can detect malware and exploits. And finally, hackers often love crash reports as a way to find perhaps exploitable vulnerabilities. So as I mentioned, and walk through some of these conceptual overviews and then dive into actually looking at specific crash reports, are if you are a user and your favorite application crashes, if you want to get it fixed, the best way is to grab the crash report and send it to a developer. And if you're a developer who is getting bug reports from your users, unless you have a crash report, it might be very difficult to actually do that. So here's an example. I'm pretty fond of Hopper. It's a disassembler or decompiler for macOS. It's pretty solid, but every now and again I'm doing weird things and it crashes. Well, when it crashes, I email the developer and I always attach a bug report. And the developer is very appreciative of this fact and says, thank you for describing the bug, but also giving me the crash report so I can track down and figure out exactly what's wrong. And then he very quickly fixes the bug. So this is great for me because then the next version of his tool doesn't crash and doesn't, interrupt my workflow. Security teams also love crash reports, and I love this story from Microsoft. So it started in 2008, and back then Microsoft was already ingesting Windows crash reports. And MSRC, the security teams at Microsoft, were classifying the crash reports looking for failed exploitation attempts. The idea that, especially with memory corruption bugs, is that unless the exploit is 100% reliable, which it very well won't be, especially if it's a memory corruption vulnerability, this may generate a crash report. If the operating system or anyone else is able to collect this crash report, they may be able to uncover the exploitation attempt, potentially uncovering a zero-day vulnerability. So that's exactly what happened in this case. They found a crash that only happened twice, and what they would do is they would rank crashes by how common they were. This one was the 45,000th crash report, so very, very rare, only happened twice. But as John, the security researcher that dug into this, wrote on the slide, they noticed by looking at this crash report, the attackers had a remote code execution vulnerability that affected every version of Windows, gave them full control at system rights, and left almost no forensic footprint, and could be used to exploit any Windows system from anywhere on the internet anonymously. Like, this is the dream if you're a hacker. Unfortunately, their vulnerability was only 98% or so, if not more, reliable. It crashed twice. Windows got the crash reports, and from this, uncovered the zero-day that was being used and subsequently patched that. Sucks for the hackers, but kudos to Microsoft. As malware analysts, we're actually also interested in crash reports as well. So a lot of times, malware will crash when it's run. And this is because it's doing really strange things. For example, it might be trying to hide its process, right? This is not something that should be normally done on a system. So compared to normal software, malware crashes, I wouldn't say often, but perhaps occasionally. This is good because we can both use this maybe as a detection metric, but also if we're trying to analyze the malware, it's really annoying if it crashes. So recently, Lockbit, which is a very prolific ransomware gang, decided to build a macOS version of their ransomware. About 6 or 7 years ago, I wrote a generic ransomware detection utility. Basically just looks for the rapid creation of encrypted files by untrusted processes. And I wanted to see if this tool could generically detect this pretty novel ransomware. Unfortunately, when you ran the ransomware on macOS, it crashed. It had a buffer overflow issue in it, which was good for users because it really meant that their files would not be locked, but that sucked for me because I wanted to get the malware to run in a virtual environment so I could test my tool. So from the crash report, though, I could figure out exactly where the bug was in the malware. I could create a patch for testing purposes only, a binary patch, and then run the malware successfully and confirm, yes, indeed, my tool detected that. So that's useful. Crash reports, as I mentioned, are also a good way to perhaps detect that malware has infected a system. Matthias gave a talk earlier about iOS. Some of the IOCs he talked about for detecting very advanced spyware was crash reports. Because again, sometimes even the best written malware will crash, especially if updates are pushed out from the operating system vendor that will change assumptions that the malware has made. So who remembers Stuxnet, the most beautiful malware ever created, right? How was it detected? Via crashes. And this was an incredibly powerful malware written by supposedly very powerful nation states and agencies, but again, undone by the fact that it crashed, generated crash reports, and led ultimately to its detection. Hackers also love crash reports. Now, they don't like when their exploit crashes, but they like when systems crash or when program crashes, because maybe those are exploitable security vulnerabilities. There's some interesting leaked documentation. I believe this came from the Snowden reports that, according to these documents, basically said that the NSA was using passive SIGINT to collect Windows error reporting. At the time, Windows error reports were not encrypted. So very easy for NSA to collect. And there's a leaked image from one of the internal documents of NSA. You can't really read it from the back, but what they have done is they've taken the system error reporting message and they changed the text on it, just for laughs, to say, this information may be intercepted by a foreign SIGINT system to gather detailed information and better exploit your machine. Hilarious. And as the documentation, the quote on the slide says, the NSA said, hey, there's two valuable pieces of information in crash reports. One, detailed information about the operating system you have and the patch level, which if we're trying to exploit you, we need this fingerprinting information, because a lot of exploits are operating system or service pack level dependent. And or if there is software on your system that's crashing from perhaps normal use, well, we're going to look and see why it's crashing to see if it's crashing by a bug that we can ultimately exploit. So now let's look at some crash report basics. First, what are crash reports? Well, as their name implies and Apple says, they're basically reports about applications or processes that crash. The idea is when something on your system crashes, a crash report is generated. Now, MacPaw has a good article kind of giving some basics, some very introductions to it. But I kind of like the main takeaway is that these crash reports are designed for developers to read. So the average user who looks at this is going to be a little confused. So what we're going to do is kind of walk through and show that the information in that, if we understand it, can be very useful to us. Now, crash reports on a Mac OS system are stored in these two diagnostic directories. There's one for the user and one for the system, and they end in .ips. You can also see them via the console. If you click on crash reports, these are all the crash reports that you can dig into. So what we're going to now do is I'm going to write some vulnerable code. I'm going to cause a crash, and we're going to walk through the crash report because most crash reports have the same format. We're trying to understand the different components of that so that when we look at other crash reports, we can figure out why the item crashed. So I have some buggy code. We can see I've declared a pointer, a null pointer, and then I'm trying to write something to this. You can't obviously write something to a null pointer. This will crash with what is known as a null pointer exception. So when I compile this and I crash, unsurprisingly, expectedly, it generates a crash report. If we click on the crash report, it starts by identifying the program that crashed, its architects, its version, and then some basic metadata, including the version of the operating system. Nothing too crazy here yet. It then also has information about the thread that crashed, including identifying the thread number. This is important because most applications have multiple threads, and generally we don't care about the other threads, save for the one that crashed. Also then is exception type information. So we have exception types and exception specifics. Here we can see that, and we don't know exactly why, imagine we hadn't seen that source code yet, that the application had crashed with a sig-seg-v. This is basically a memory access violation. And in the exception code, we can see that it says invalid address at 0. The exception codes are going to be unique to the exception types. Next up, we have a stack backtrace. Kind of have this diagrammatically on the left-hand side. This basically shows or tells you the control flow. What happened? How did we get to the instruction that actually caused the exception? So in this stack trace, what you have are stack frames, except for the very top of the stack trace. That is going to be something known as the faulting instruction. And this is very important because this is the actual instruction that caused the crash. So what we're going to do is obviously take a look at that. But normally then you look at the stack backtrace to figure out, well, how did we end up here in the first place? The crash report also has the crashed thread state. This is the state of all the registers and their values that happened when the faulting instruction triggered the crash. And this is very useful, especially if you understand the meaning of the registers. So this is from a ARM64 system, so we're dealing with ARM registers on Intel. Obviously, the crashed thread state would include Intel-based registers. You have a wonderful book written by Maria that explains these all, but I have a table on the slide that explains some of the basics. So for example, x0 through x7 contain the first 8 arguments to a function. So if you find a crash at the beginning of a function and these registers haven't been overwritten yet, well, now we just have the value of the arguments that were passed in. And this context can be very helpful in figuring out ultimately why the crash was triggered. Also, the crash report will have the list of loaded binaries, including the main binary and then any subsequent dynamic libraries. This is most important to us because it's going to give you the in-memory address of the binary images. This is important because when executables and dynamic libraries are loaded on macOS, they are ASLR'd, which basically means the dynamic linker and loader moves them around in memory. This is an exploitation mitigation to prevent guessing memory addresses. But this is a little problematic for us because if we load the application that crashed in a disassembler, its memory addresses and where it was loaded in memory are going to be different. So what we do is, because in the crash report we have the memory address, is we can take that, and then in the disassembler we just tell the disassembler to please rebase the image. And this is how you do it in Hopper, pretty straightforward. We give it the base address of where this, for example, application or program was loaded in memory, and once it's been rebased, the addresses in the disassembler will match the addresses in the crash report. Now, I mentioned this faulting address. This is, again, the address that triggered the crash. So we grabbed that from the crash report, and now that we have the crashed application or program in a disassembler and rebased it, we can go there and see exactly what that instruction was. So the crash report is not going to have the instruction. It's going to have the address of the instruction. So again, in a disassembler, we can go see what that instruction is. I'm not going to read through all the ARM disassembly, but basically we can see it's a store instruction, and it's trying to write whatever was in the W8 register into the X9 register, or rather where the X9 register pointed to. And if we look back a few instructions, we basically can see that the X9 register was loaded from the var18, and var18 was set to null. This again maps back to our source code. So again, the crashed instruction is right here, right? Star A, dereferencing A, putting in 41, is the same thing as storing W8, which was set to 41 right here, into that null pointer. So now we've just, again, confirmed that, yes, where it crashed was this line of code. Okay, so that hopefully gave you a decent overview of crash reports, right? You have faulting instructions, you have crashed thread state, you have loaded binaries, et cetera, et cetera. So now let's apply this knowledge to some real crash reports, caveating two things. First, these are solely from my computer, And secondly, they are solely from normal use. I'm not fuzzing anything. I'm not trying to perform any of the attacks that many people were talking about earlier. And so I think that's interesting because, as we'll see, some of the bugs are actually problematic, security issues. Now, I did mention at the beginning that developers love crash reports. And so the first crash report I want to talk to you about is not a security bug per se, and it was actually not in macOS. It was actually in one of my own applications. But as we can see, or will see, from the crash report, I was very easily able to figure out what was the problem in my software and then ultimately fix it very quickly. Whereas if I didn't have a crash report, I might still be trying to figure it out to this day. Okay, so Lulu, open source firewall. I ran it. It was doing great. Then all of a sudden, it crashed. And I looked at the crash report, and I noticed that the exception was given was a SIG bus error. A SIG bus error basically means that the CPU could not physically even access the memory. So it wasn't like a memory access violation. It was like there's no memory there. The other thing I looked at was the call stack. And we could see it's a huge call stack. There are 328 frames. And if we look at the call stack, we can see a repetition of the same function. So we have a SIG bus exception, a repeating call stack. This generally looks like call stack exhaustion, probably due to recursion. And as soon as I saw this, I was like, oh man, I know exactly what happened. So Lulu has this idea of related flows. So imagine you install Lulu, it's a firewall, you delete all the default rules, and then you open a browser that says maybe has 50 tabs open. Lulu is going to see 50 connections from that browser. Now, if it doesn't have a rule for that browser, it's a firewall, it's going to ask the user, hey, do you want to let Safari access the web, Chrome access the web? Now, it shouldn't ask the user 50 times all at once. So what Lulu does is store all the related flows that are network connections from that same process, and then waits for the user's response. If the user says allow the browser, all of the related flows are then allowed. If the user says block, they're all blocked. It's a little more complicated, though, because what if the user says, allow this first connection, but only because it's to objective-c.org? Okay, in that case, what Lulu has to do is then process the next related flow, and if it's different, for example, connecting out to Google, show another alert that says, okay, well, what about this one? And so what I thought I would do, and I thought this was super cool, is I would handle this recursively. So anytime the user responded, I would just handle the next recursive flow and continue on, and the recursion would end when all the related flows were processed. And I said, well, how many related flows could there be? Well, it turns out, imagine you restore your browser with several tabs open. Those are going to generate tons of connections. And what happens is when you get 300 or so connections all at once, Lulu is recursively going through this. This is going to basically run off the end of the stack. Because every time you make a function call, and right here we can see we call process event, which itself calls process-related flow, recursively, information about the process and the method call is pushed to the stack. And the stack on macOS is apparently pretty short. So if we have too many related flows, we basically fall off the stack. And it's kind of like, not a stack overflow, but like a stack exhaustion. We basically run out of stack space. So from the crash report, I very easily could see it was a recursion issue. I'd written this code, so I immediately knew what the issue was. And of course, the fix was just to move from recursion back to iteration. So I still never have used recursion successfully in my life. The next bug was also in one of my tools, but as we'll see, this was not my fault. So I wrote a tool called Do Not Disturb. The idea is if someone opens your laptop, it would take a picture and send it to your phone. So if you were wandering around in Russia and someone was doing an evil maid attack, you would get an alert. So this was all well and good, but I noticed it crashed. And again, I didn't know why it crashed until I looked at the crash report. So if we look at the stack backtrace, we can see that, yes, this seems to be triggered by Do Not Disturb and its D&D framework, but ultimately the crash is in the sec error function in the security framework. If we look a few lines back, we can see that the first call in the security framework is this sec key copy public key. Here's the code in D&D that's calling that. And this looks like a pretty standard API, and so I was like, I don't think I'm calling this incorrectly, so let's dive into the security framework and see what is going on. So if we do that, following information, we can see that thread 6 has crashed. We have the address of the faulting instruction. We can load the security framework into disassembler, rebase it so the addresses match, then go to that address, and we can see the faulting instruction is a invalid pointer dereference, and this is Intel base code. Luckily, the security framework is open source, so what I can do is I can load the source code and then basically figure out what line of source code matches the assembly instruction, because it's way easier to read source code than assembly, especially when you're trying to track down a bug. So here is the line that was crashing, cf error ref, previously error equals star error. So okay, we see that this is crashing because it's an invalid garbage pointer. Its value is 1. Obviously, you can't dereference and store something at memory address run. We don't know why yet, but we're making progress. So again, I went back to the source code, and if we look at where this code is, it's in the copy public key API. We can see there's that error pointer that essentially is garbage. At the bottom of the function, they call this end sec key API macro. If we expand that macro, we can see that they are invoking that sec error API. And so what I did was I copied and pasted this code into Xcode, and Xcode actually points out exactly what the problem is. It says variable error is uninitialized when used here. Initialize the variable to fix the error. So if we look at that, we can see that yes, indeed, they've declared a pointer, but they've never set it to anything. So that then when they try to use it, you can't use an uninitialized pointer. This will crash. So I reported this to Apple, mostly because I just wanted my tool to run. Apple graciously gave it a CVE. And then I said, okay, this is an interesting bug. Let me write a blog post about it, because maybe this experience will be useful or educational to other people. So I posted that, thought it was great. And then an Apple employee weighed in and basically says, normal bug report, hey, you have a bug here. Security researcher bug report. 10,000-word Telemundo soap opera about how the bug was found, and hey, how I'm smart and you're stupid. All right, thanks, Apple. Maybe this is why there's some, hostility between external security researchers and Cupertino. I'm just trying to get software to run. Maybe you fixed your code. Speaking of problematic bugs, around the same time I was developing ransomware, which we showed earlier is the generic ransomware utility to detect ransomware. And again, I was running it, and I came back from being out and about, and my system had panicked. Now, I'm a little strange. Whenever my box panics, I get excited, because I'm like, is there a kernel bug here? And in this case, we will see there were several. So we have a kernel crash report, and we can see information telling us, for example, that there was a page fault, and also the memory address where the page fault occurred. Also, it says that the current process was syslog. So like, syslog panicked the box? What? Strange. So what we do is we have the address of the faulting instruction, so we can load the kernel into memory, go to that address, and see what happened. There we have an instruction, and what it's trying to do, it's trying to compare some address with 0. And that address is in RBX plus R13 plus 2, and we'll dig into what those registers are. Again, this part of the kernel was open source. That was great. So what I could do is I could figure out the exact line of code where the crash occurred. And it turns out it's in an audit function. This is why syslog triggered the crash, because it was trying to audit something and write it out to an audit log. And if we look at what it's doing, it's basically trying to check that the path of a Unix socket ends in 0 or not. So basically, it's trying to check if something is null terminated. And this is because Unix sockets don't actually have to be null terminated. So before they, perhaps maybe do a string copy, they have to make sure it's null terminated. So they're just doing a check. So since we have a lot of thread state, which again is the context of the registered at the time of the crash, we can take those values and see what they are. So again, we have the faulting instruction, compare byte pointer, blah, blah, blah. This mapped to source code, where they're checking the path is null. We can then input the values of RBX and R13, and if we add those up, we get an address that ends in F000, which matches the address that triggered the fault. So in other words, we basically just confirm that we are on the right path. This instruction is apparently trying to access some invalid address, and based on the register values that we add up, it's invalid. So what this means, what was happening is that when they went to check, and this is the details of the bug, if the end of the string was null terminated, they had a very subtle off by 1 error. So if you think about an array, imagine the array has 3 items in it. Well, computers start counting at 0. So that means the first item is going to be in index 0, the second one in index 1, and the last one in index 2. This means if you try to check the end of the array, you should use the index 2, not the value of 3. So the problem is they were using the length as an index, going 1 past the array. Now normally this was fine unless the address of the memory that came right afterwards was unmapped. And in this case, when they then try to read what they wanted to do is read the end of the array, since they went off by 1, this would now fall into an unmapped page. And if you try to read an unmapped page, this is going to cause a kernel panic. So it's kind of standard off by 1. So again, I reported this to Apple. I was like, hey, kernel bug. This isn't really a security issue. It's just panicking the box. It's not a memory leak. It's just, an annoying bug. And Apple's fix was to add a strl copy. This is insane, because if you look at the comment, it says, make sure the path is null terminated. So this is what they were trying to do, because again, Unix sockets don't have to be null terminated. If you know what strl copy does, it's going to copy as many bytes as it can until either the buffer fills up or it finds a null. So in other words, you should only call this on a string that's null terminated. If you're not sure if it's null terminated or not, you should not be calling this. So Apple's fix for this off by 1 error was to introduce a kernel memory leak. So here we can see an example of that. If you call now strl copy on a Unix socket, and you can create a Unix socket without a null terminated path, it will start randomly reading memory from the kernel and nicely write it out to a log that you can grab from user mode. So Apple's patch for their off by 1 bug, which was just an annoying kernel panic, was to actually introduce a kernel memory leak. Hooray, I guess? Better than a bounty, right? So I said, okay, this function seems problematic. The fix is absurd. What else is going here? So I looked a few lines up, and again, this was the function that was causing the kernel panic, and I noticed that there was an unbounded B copy. So what they were trying to do was copy values from a user-controlled socket into a buffer that was only 128 bytes. Now the problem is you can create a Unix socket that has a path that's longer than 128 bytes. So instead, this is a vanilla heap overflow in the kernel. And we can see diagrammatically what it looks like. You can basically create a socket that has more than 128 bytes in its name. They'll come along and try to audit this socket. It'll cause a heap overflow and allow us to control a lot of variables that ultimately, if we take this further, would lead to a full system compromise. So again, I was like, okay, Apple, this is getting a little silly. Please fix this. You're introducing heap overflows and memory kernel leaks. And they said, yeah, cool, thanks, fixed it as dupe. And I was like, cool, I'm not chasing CVEs, but at least maybe you should let people know in the security documents that you fixed a kernel heap overflow. But Apple is Apple. So now let's dig into a lot more recent crashes that were in Ventura and in Sonoma. And again, these are all from my system, and again, just from normal use. So the first one was in Safari. I was browsing around, Safari crashed. I was all excited because I was like, oh, maybe it's an exploitable bug. Well, if we look at it, we can see it's an invalid access. We look at the address, it's 68. Whenever you see an invalid memory access with a low number, it's probably a null pointer exception. If we dig into this a little more, we can see that, yes, they are basically trying to load something from x0 plus 68. And if we look at the kernel thread state, we can see that x0 is set to 0. So when they take 0 and add 68, this is how they get the value of 68. 68 is essentially null. It's not valid memory. So when Safari tries to dereference it, it crashes. So basically, this is a bug in Safari. They are getting an object back in this wcage page copy page configuration API. They're not checking if the object is null, and then it crashes. Now you might want to look into this closer. Maybe the object has been freed and overwritten. But in this case, I think it's a pretty standard null pointer exception. So maybe not something that's exploitable per se. The next one is in the shell, and this one was hilarious, to me, because I was actually testing another exploit. And this was the exploit I talked about yesterday, where I needed to suspend the BTM agent so that then I could persist malware without any alerts being done to the user. So I was testing this, it worked really well, the agent was going to sleep, I could persist and bypass Apple's BTM alerts, and then I would kill or resume the agent, and then the shell kept crashing, which to me was strange because I was sending signals, like not to the shell, but to the BTM agent. So like, why is the shell crashing? If we look at the crash report, it's kind of interesting. It says possible point authentication failure. So this to me points to a memory corruption or a use after free vulnerability. Also, if we look at the thread stack, we see it being triggered by the sigtrap handler. And this kind of makes sense because I was sending signals to other processes, but also signal handlers are notoriously complex. You're in this like weird state. They're not supposed to be, or generally aren't thread reentrant, et cetera, et cetera. They're hard to get right. So in a way, this wasn't surprising to me that there was a bug here. So let's dig in a little closer. Again, taking that faulting address, and because the shell is open source, we can then map it to the actual instruction and function where the vulnerability lies. So basically what they're calling is this get link node. This is always where it crashed, and this would crash pretty consistently. And what they were trying to do is get an object that began from the start of a linked list. And if we look at the instruction in the crash report, and it's kind of chopped off at the bottom, the problem is this object appears to have already been released or freed, or has now been overwritten, and this is likely because multiple signal handlers are being called at once. So this linked list does not appear to be synchronized or allow for multi-threaded applications, but again, because of they're doing these weird signal trapping, this object is getting corrupted. An interesting bug, but you know, it's the shell. Like, you're not going to really like exploit the shell, but something annoying, and maybe to be aware of if you're using the shell to throw other exploits. The last one I want to talk about impacts Xcode, and specifically Apple's notarization service. Again, this happened when I was creating software, and Apple now says, before you deploy software, it has to be notarized. And I was like, okay, cool, I'll give you my $99, and yes, I will submit it to your notarization service. I will wait for you to notarize it, and yes, you also are notarizing malware, so like, okay, but we'll deal, right? We'll play by it. So I'm doing this, and then like, Xcode keeps saying, couldn't communicate with helper application. And I'm trying to push out an update, and I'm like, Apple, what gives? So I'm trying to figure out what's going on, and I'm like, let me look at the crash logs. And I look at the crash logs, and there's two crash logs. There's one from Xcode, and there's one from the com.apple dt Xcode iTunes service, software service, which I'll refer to now as the notarization service. It's actually the helper application that talks to Apple's notarization service to perform the notarization checks. So what was happening was that the notarization service was crashing, which in turn would cause Xcode to crash. Xcode was written in a way that if this helper application crashed, it couldn't handle that, so it would crash itself. So what we're going to do is just focus on the notarization one. It's a little more interesting. Again, if we look at the information from the crash report, we can see it appears to be a memory corruption or memory issue that leading, again, to possible pointer authentication failure. So if we look at the crash reports, and there were multiple crash reports, this happened pretty consistently, they always crashed in two places, specifically in a call to either obfc message send or obfc message release. And if we look at the call stack right behind it, so call stack number 1, we can see that this is always in the get status function. So let's take a closer look at this get status function. We load it in a disassembler, and as I mentioned, this would crash, but always very close to itself. So not necessarily on the same line, but always within the same function, and specifically at two places. Either at a call to obfc message send, invoking the close file API, or when obfc message was send was called to release an object. And I've created the Objective-C code to show these are the two lines that are always causing the crash. And what we can see is actually that object is the same. Now, if you see a crash occurring in an obfc message send call or a release call, this means that that object has either been corrupted or has been freed but is still being referenced. So let's dig into that a little more. So we need to first find out like what object this is so that I can find more information about it. And I had an assumption because the first call to the obj message send was invoking close file, which you're going to do on a file handle. So I debugged the application because it wouldn't crash all the time. The notarization service ran sometimes. And what I could see is when I set a breakpoint on this, I could confirm that, in fact, this was indeed a file handle. And if we look at the variable name, it's in a function called majestic log file handle. So it's not any file handle, it's a majestic one. I don't know what that means, but that made me laugh. If we dig into it a little deeper, we can go back to the crash report, and even though thread 2 had crashed, we can see that there are other threads, specifically thread number 1 and number 4, that if we go back in the call stack, we can see they're all calling this notarization status response method. And this method, as we can see on the slide, is the other threads are concurrently executing logic within the notarization status response, meaning they've already invoked that get status function. And what was the last thing that get status function did on that did on that file handle? It called release, right? So again, I went and set a breakpoint on that, and what happened is, as soon as I set that breakpoint, the debugger actually hit on 2 threads concurrently, which basically means 2 threads were trying to access that same file handle, and as we just showed, multiple threads had already actually gone through and released it. So this just appears to be a use after free vulnerability where another thread has already released that file handle object. The other thread that's still using it comes along to close it or to free it, which causes a crash. So a kind of standard use after free vulnerability. And of course, there's many more. And again, this is just my computer. So, maybe the Russians are trying to hack me via Bluetooth and Keynote and Messages, Windows Server. Or maybe, software on macOS crashes a lot, in some cases with exploitable security vulnerabilities. My favorite one, and I haven't looked into this one yet, is the console application. That is the app you use to look at crash reports, which is crashing itself. So some like meta crashing going along. Okay, so let's wrap this all up. So first, I really want you to leave with a deep appreciation of crash reports because, they are your friends. If you are a user, you're going to want to send the crash reports to the developer because this is how the developer is going to figure out what bug. People always say, "Oh, Patrick, your software crashed." I always say, "I'm sorry. It's free. It's free. I'm not a software developer. But please send me a crash report because this will have the information that allows me to patch it." If you're a developer, crash reports are also your friends because, as I just mentioned, they have the information for you. However, I think that crash reports are also very useful for a myriad of other ways that we walk through. If you are looking for security vulnerabilities or bugs, crash reports may have that. We showed, for example, some of these crash reports led to uninitialized pointers, use after freeze, or in some cases, exploitable kernel heap overflow. Also, if you have a security product, crash reports may be a good detection mechanism. I mentioned malware often crashes or occasionally crashes, and so this is a good way to find, especially perhaps on iOS, as Matthias mentioned. So that is a crash report. I want to end with a survey. Who loves crash reports now? Okay, awesome. I should have asked this at the beginning, but I feel like I have instilled this love upon you, and so my job here is done.